Hey guys, this is the solution for the AP Physics C Mechanics Unit 2 Review Practice Free Response question number 2. Let's go ahead and get started. Okay, so in this question, it tells us we've got a cart with an elastic cord, and the elastic cord is going to stop the cart. So the cart's going to be given some initial speed. And so it tells us that it's given an initial speed of 2.0 meters per second. And it moves with this constant speed until the elastic cord exerts a force on it. And so the motion is measured with a sensor. So we've got the velocity versus time, which we're getting from the motion sensor. And then we got a force versus time, which we get from the force sensor. So this is real similar to the lab that we did earlier in the year. Both sensors are set up so that positive direction is to the left. So this way to the left is considered positive that way. All right, so the first question says calculate the mass m of the car. All right, so this is pretty easy. The mass, what we'll do is we'll use the impulse momentum theorem. So we can set it up to where it says delta P, which is the change in momentum, is equal to mv final minus mv initial. Well, that expression is also what's known as the impulse. All right, and so the impulse is given to us from the graph. And so right here, this graph shows us that the area of this little shape is 1.0 Newton seconds. And so the impulse itself, which sometimes we call J, is equal to 1.0 Newton seconds. So what we can do is we can set our change of momentum, mv final minus mv initial, to our impulse. And so I'll just set that up to where I say 1.0 is equal to our impulse, mv final minus mv initial. In this case, we can look at our graph to find out what our initial and final velocities are. Our initial velocity is -2, so I'll substitute that in. And in fact, let me factor out the m out of this. It's a little bit easier to do it that way. Our final velocity is actually going to be 2, and our initial velocity is -2. And so when we solve for m, we get the mass is equal to 1/4, or in other words, 0.25 kilograms. All right, that's solution for part A. Now part B, it goes on to tell us that for time period from 0.5 to 0.75 seconds, which is this interval that they tell us, the force F of the elastic cord exerts on the cart is given as a function of time by this information. And so it says using that given equation, show that the area is 1 Newton seconds. All right, so this is where to find the area, of course, you use an integral. And so to find the integral of this function, that will give us the impulse. In other words, it's trying to verify that our impulse is 1.0. So the impulse is the integral of the force function with respect to time. All right. Now it does give us limits. It does tell us that we're going from 0.5 seconds to 0.75 seconds. And it tells us what our function is. It's a sine omega t. That's what this f is, a sine omega t. And we need to evaluate the integral of that function. Now it does tell us what a is. It's 6.3. And it tells us what omega is, 12.6 t. So I need to take the integral of that. All right. Now this has a form of the integral of sine a of x. Now this is an integral that is typically not memorized, but I think it's on your equation page, and you can just look it up, where your integral is going to be negative 1 over a cosine ax. That's what the integral rule is for that. And so when we plug those, when we make that substitution, our 6.3 I can pull out, and it's going to be multiplied by negative 1 over a being this term in front, so it's 12.6, times the cosine of 12.6 times the time. and that is going to be evaluated between 0.5 and 0.75. All right, so it turns out that 6.3 divided by 12.6 is about 0.5, and we got a negative sign here. So we got negative 0.5 times the cosine of, we'll do our upper limit first, 12.6 times 0.75 minus, and this is our lower limit, cosine of 12.6 times 0.5. And when you evaluate this and make sure your calculator's in degrees mode, you'll see that these numbers here correspond to 0 and 180 degrees on a unit circle. And so, or 90 and 270, I believe. I can't remember. I might be messing that up. But at any rate, this term right here reduces to -1. Okay, yeah, so that'll be 180 degrees. And this term right here reduces to +1, so that's like at 0 degrees. And so you end up getting negative 0.5 times -1 minus 1, which is -2. So you got negative 0.5 times -2. And so sure enough, you get 1.0. And so that's verification that indeed our impulse is 1.0 Newton seconds. Now question C says the experiment is repeated with a different core that exerts a larger force on the cart. The cart starts and ends with the same speeds as those in the original experiments, and that's really crucial to know that these velocities, v initial and v final, are the same. And the question says, will the area for the graph of the force function of time for the new chord be greater than, less than, or equal to? Well, the correct answer is going to be equal to. And the reason why is that because we're given information about the initial and final velocities, v initial is going to be -2 meters per second, and v final is 2 meters per second right here. Then that means our change in velocity, delta p, which is m v final minus v initial, is going to be the mass, which we calculated earlier to be 0.25, times our final velocity, which is 2, minus our initial velocity, which is -2. We end up getting that our delta p is 1.0. Well, that's 1.0 Newton seconds. That's the same thing as our impulse, which is the area. Sorry guys, I'm off the page here. 1.0 Newton seconds, which is the impulse, which is the area. And so sure enough, there's no change for that graph. So it has to be equal to the original equation that's up here. Now what's going to happen is that graph is going to change. The area doesn't change, but the graph is going to change. And so like if I were to repeat this experiment with this stronger elastic cord, you would have a similar kind of shape, but it's probably going to come up here and going to be a little bit spikier. It's going to occur over a time interval that's less than. The average force will be greater than, but the area of the shape won't change. It'll still be 0.1 Newton seconds. That's kind of hard to see. But the idea is that force function is now kind of a spikier graph than it was before. The area still being 1.0. All right. Now question D says to derive an expression for the maximum change in length of the cord. All right, so this is actually a conservation of energy style question. Easiest way to do this is to set it up as my initial energy type has to equal the final energy type. And the reason why we know we can do that is because it tells us the cord from the original experiment can be modeled as an ideal spring, and ideal springs conserve energy. And so that means that this initial energy type will be the elastic US for spring type of potential energy. And of course, our final energy is going to be, or sorry, I've got these backwards. Our initial energy type is going to be our kinetic energy, and our final energy type will be the elastic potential energy. Sorry about that. And so we just substitute our values in. 1/2 m v naught squared, tells us to use v naught, equals 1/2 k times x max squared. Because all this potential, or this kinetic energy, will turn into stretching that spring to its maximum length. And so all we need to do is solve for x max, and we get x max as the square root, or as v naught times the square root of m divided by k. So that's for part D. Now for part E, it switches up a little bit, and it tells us some information about some an experiment where they do different trials with different masses on it. And for every addition of mass, you get some more stretch length. And that kind of makes sense. It's got more inertia, so it's going to stretch further. And the question says, indicate below which quantities should be graphed to yield a straight line with a slope that could be used to calculate a numerical value for the force constant. All right, so that's pretty straightforward. And the way I usually set these up is I go back to the original equation that I use to see how your mass and your stretch length works with each other. And so if I look at that, we set it up where we had 1/2 m v naught squared is equal to 1/2 k x max. And the question is wanting to know, how would you rearrange this, or what would you plot to get the force constant? So I'm going to take this equation and solve for k this time. So the 1/2's go away, and so k is going to be our mass divided by our x max squared times our v naught squared. All right, and so here's the thing. What's constant in this formula? Well, v naught is constant. What is varying? Well, the mass varies. It tells us that the mass of the cart is being changed. And as a result, the distance that the spring stretches, x max, also changes. So these two things are variables. One's an independent variable, one's a dependent variable. Now, so what we want to do is we want to say, well, what should I graph to be able to get k? It doesn't say to actually do it. It just says, what should I graph? Well, you don't want to graph a constant. That's kind of dumb. Later on, when you do a calculation, you can multiply by v naught squared. But if I graph mass m on the y-axis and graph x max squared on the x-axis, then that would correspond to this kind of equation. This would be like a y over an x. All right, and so that's what I'm going to do, is I'm going to graph those two terms. All right, now it does say use the columns in the remaining table, or remaining columns in the table as needed to record any quantities that you are not given. So on my own, I calculated the x max squared and I wrote those down. Okay, so I just squared these terms and rewrote them. And then on the next part says to plot the data points for the given quantities drawn in part E. Clearly scale and label all axes, including units, as appropriate. Draw a straight line that best represents the data. So this is a pretty typical plot the data points, draw a line of best fit, and you'd be expected to do that by hand, and you would get something similar to this, where I have x max squared on the horizontal axis, and I've got mass in kilograms on the vertical axis. And so by hand, what you would do at that point is you would go ahead and calculate what the slope is. And you would get around 9.6 for something like this. And so that leads us into part G, where it says use the best fit line to calculate the force constant. It doesn't say to plug something into an equation. It says use the best fit line. That just means use the slope. If it tells you to do that, that means, yeah, use the slope. And so that's pretty easy enough. Now that we have our equation kind of set up for us, we can calculate the slope, or we've already calculated it using the, I use the Excel. You could use your calculator if you wanted to. But we came up with our equation was at, K is equal to M over X max squared times V naught squared. Well, this term right here, this is our slope times V naught squared. And so for my calculations, I got 9.632, or sorry, 632. That's my slope. And our initial velocity was 2. So that's 2 squared. And so when you end up calculating this, our very last answer is going to be 38.528 newtons per meter. Now, since you're going to be doing this by hand, probably on a test, if you don't have a calculator or you don't want to do it by calculator, you're going to have a range of values, but anywhere close to that, they allow a range of values for being correct. All right. Now, guys, that concludes this question. If you do have any kind of issues or you need to get more clarification, just send me an email, and I'll be glad to help you out. All right, guys, thanks a lot, and have a good day.